There might be some issue, but yeah. Anyway, so let's get started then. Okay, so this topic is analysis. What is the plan? Like, how are we going to get started? And what's the plan for today as much as we can do? So really, before we get started to do analysis on sets, right? So we are basically going to do analysis on sets. Okay, what sets? We are not going to do it on any sets, right? We are going to do sets in R, maybe, right? And later on, we'll study functions and such. We'll see that sequences really come in the middle as a matter of like, because studying sequences is easier than studying random sets. And studying sequences also turns out to be enough. That's thanks to the way R is constructed. So we will see what that means. Okay, but really, this topic, as you know, started from calculus. So we would have to start from like a physical, thing. The need for why we studied certain kinds of subsets in analysis. So really, as all of you know, right, it really started from problems in physics, right? Problems in physics. So we're not going to discuss them, but I'm just saying that, right, there was some particle moving with respect to time, in a certain way, in a certain locus, as you all will know, right? So what I'm trying to say is that, let's say there is from time is from 0 to 10 seconds, and let's say a particle is moving like this. And we're just trying to study the motion of the particle, right? We are trying to maybe describe at what time t was the particle at the highest point, okay, or what time t it's at the lowest point, or when is the speed the highest. Certain kinds of questions like this is what we are trying to study. We are trying to track a point right, basically tracking a locus, studying the locus, right? Studying, tracking a point. Okay, now realize this, that when you are tracking a point and when you're studying the motion or evolution of something over time, right, then basically this element of time here, this is a continuous entity, right? It's a continuous entity. I'm not saying the function is continuous or not. I'm not going into that. I'm just saying that this subset over which we are studying, okay, is a continuous entity. So it's kind of what we call continuum. There are no gaps in between. Now, what are gaps and such we'll describe, but that's a feeling, okay? So continuum, they don't have gaps. So these are the sets which we will be interested in, okay? So these are the good sets in R, good sets in our real numbers. We will also describe what the real numbers mean, but basically we'll want to study these kind of sets which don't have gaps, okay? And also we would like to have our sets, it would be good if our sets would have maxima and minima, right? Because good things happen that at those points, right? So these are the kind of sets we will be interested in. For example, if you're going to do arithmetic, or if you're going to do algebra, for example, those of us who have done vector spaces, or any kind of algebra, so there, whatever set you are interested in, so maybe just aside, in algebra, what are the interesting sets, right? If you're studying vector spaces, then the interesting sets are subspaces, right? Why are they interesting? Because in subspaces you can have some kind of arithmetic, isn't it? Or in groups are interesting, again, it's interesting sets, because there you can do multiplication and still remain inside. Here also we would want our sets to be like not having any gaps, having some maxima minima, if possible. If not possible, we'll have to look for an alternative, things like that. Okay, so let's see then. So now we have kind of a motivation of what sets to look at. I mean, although most of you would have already looked at such sets, but we can probably look at it. Probably now we are seeing it in foresight rather than hindsight. Let's see. So first of all, if we start with the natural numbers, so I will not define the natural numbers. We will assume that we all of course know it, but definitions of it are actually a little difficult. You have to go into piano arithmetic and all that, but we are not going to build it from that much of a foundational level because we don't have that much time. So we'll just assume what n is, okay? And obviously, on top of that, we also have the rationals, right? So Can anybody define what this subset, what define the rationals? Let's see. Because we really study the rationals closely, see where they are adequate and insufficient and so on. Let's see. So can anybody try to define what the rationals mean? Yeah, anybody wants to try it?
Means rational numbers.
Yeah, defining rational numbers.
Then we can say numbers of the form p by q that way,
Yes, you can say numbers of the form p by q such that,
where q
uh,
belongs to natural number and p
and
is in z.
yeah, GCD of p and q is 1, right? So you can give this kind of definition of the rational numbers. This is certainly not a bad definition, okay? But the problem with this kind of definition is that really you would have to then describe what is the meaning of this term. And if you think very closely, it's not that simple of a job to describe it. We assume that we know it, but then you have to describe that and so on. So there, I mean, that can clearly be done. However, there is an alternative also. And this, for those who have done linear algebra with me, I also define vectors in a similar fashion. I will show you how. So you start with the core, and the core is n. So you take n cross n, and this is essentially a nice way to see again. So you take n cross n, okay? And now, so what I'm trying to say is I'm trying to view q in terms of n cross n, okay? So that's what I'm trying to do. So I've got we can see it, we can see this by density property. Um, can you describe what you mean, Cyan? Density property in this case, density property. No, but our question is more fundamental, right? We are trying to understand what this P by Q even means. How do you describe it? Hmm. Yeah, or maybe you can just take it as I'm just trying to write an alternative definition. Okay, so by density property, I don't see what you are saying unless you try to describe it. Density property is definitely important, but first of all, you have to put a sense of order on Q before we even define density property. Okay, so anyways, see, when you say P by Q definitely makes sense. Intuitively, we all understand what it means with the fractions and such, right? But to define it really, it's not. It's a little, yeah. If you think about it, um, it will be longer than you think to describe it. Okay, so we are trying to. So what
By
my
taking a copy of a direct product of natural numbers
mhm.
with GCD of those natural numbers being 1.
Exactly, yeah. So you can view it like that, yeah. So then again, you will say that Q is a subset of n cross n. Yeah, that's basically where I was getting. That makes sense to me. Yeah. Q is a subset of n cross n. Okay, such that, so this is a relation, it's a relation on n cross n. And this is described by a comma b where, GCD of a and b is 1. Yeah. This also is a very good definition. Yeah. But another thing with this definition is this is also not a set theoretic definition. It involves a bit of numbers, number theory in it because the GCD thing is there. So to really, if you really want to get rid of that as well, then you can do the following. Okay, but this definition is, I feel it's more set theoretic. Okay, however, like alternative definition is you take n cross n and then you put an equivalence relation on it. Okay, and really now you will see that this is the way I had defined vectors also. So maybe as an assignment, I can ask people to define vectors using an equivalence relation because that is really a very good way to define things. In general, in maths, things are defined by using equivalence relations. Let's see, and the equivalence classes that are formed from there. So you put an equivalence relation on n cross n, okay, as follows. So you say that sorry, I mean it's an equivalence relation on n cross n. So we say that. So can anybody describe what the rule for this relation should be? Yeah. because we all know what we are trying to do, right? We are just trying to say that the GCD is 1. So, I mean, in sense that we are trying to say that 2 by 4 is same as 3 by 6. Okay. So that basically comes down to saying that if the rule is if A times D equals to B times C, isn't it? This is the equivalence relation we are putting on n cross n. Now, if you look at this definition does not use division. It actually defines division. You can actually define the in division and inverses by this thing, right? You can define inverse of 2 as using this equation. That's why on a definitional level, this is the only correct definition. I mean, the other definitions are also correct, but yeah, there are, it depends on how precise one wants to be. Okay, so does everybody get what I'm trying to do here by putting this relation, right? And then Q is the equivalence classes under this relation. Q is the equivalence, equivalence classes. Consider them as elements of this relation. Okay. For example, I mean, half is the number which is the following class. Half is a number which is basically this class. It's this class where you have 1 comma 2, 3 comma 6, 4 comma 8, and so on. This class, I mean, the fact that this is an equivalence relation is something that you can check. If anybody has any doubts, please ask me now. There's no problem, because I don't know who has done equivalence relations and who may not be, if I'm remembering it well, and so on. Okay, so this is the definition of Q that is really built from the core without introducing new operations. It's just based on multiplication. Okay, yes, so I guess this is fine. Now let us, but we all understand what Q is, so we will use it as we know it. Now let us look at the problems that Q has, and let's look at the good and the bads of Q. So first of all, as I said, that the sets that we are interested in must be kind of continuum. Okay, so what I mean is that if S is an interesting set, if S is an interesting set, so I mean interesting in the sense I think people understand, kind of, in analysis sense, then it must have the following property. But before I state that property, we will assume the order that we have on Q, the order relation that we have on Q. Okay. Now, you see, if you think about it, the order thing is another kind of a relation, right? So maybe before studying the property, I'm sorry, I have to just digress a little bit to define what the order relation is. So order relation, or maybe I should say total order relation, but order relation on a set S. Why am I doing this? Why don't I just continue from here and just write Q and try to study it? I'm trying to see if, I mean, I'm trying to say things just on the level of sets without any concrete. I mean, I'm showing the examples of concrete, and of course, people are imagining Q in their heads. But I'm trying to also do things as much as possible in an abstract way, so that later on, when you meet other kinds of objects which are like Q, you can apply the same theory because they will all have the same property. So you don't have to do analysis, let's say, on function spaces again. If you're studying functions, where functions will be, every function will be your element. So things like that is why I'm trying to be a bit abstract. So order relation on set S. So I'm sure some of us might have seen what order relation means. So can anybody try to define what order relation on a set means? Yeah, anybody has seen it? Okay, so nobody wants to say. Okay, so really what it means is, again, it's a type of relation, right? So for example, if you have the natural numbers, we have one comma, maybe we have this one less than two, two less than
Basically, a
three.
relation on a set which is obviously
Mhm.
reflexive.
mm, Reflexive, okay, yeah, reflexive. So relation on a set, you mean relation on, uh, I mean, you mean on S cross S.
Yeah, I mean a binary relation.
Yeah, right. So then you are perfect. Yeah, a binary. Yeah. So order relation, okay, is a relation on S cross S Okay, a binary relation. Both now it's very clear is binary because it's just on S crosses. Yeah, go ahead. Uh,
Which is reflexive,
okay,
transitive, and antisymmetric, I think. Uh,
transitive. Yeah, of course, right. Antisymmetric. Yeah. So I am not going into many details, even though order theory itself is a very nice branch. Okay, nice, interesting things. We'll try to see patterns of. We'll try to see, its uses here in analysis. Also, we will do that. But for the time being, these are the three properties. Antisymmetry. Does everybody understand? Can Anish, if you're saying, can you just describe antisymmetry for us? Or Subham is saying, yeah, or whoever is saying, who was saying.
Antisymmetry means if we have, say, let us take a pair A comma B.
Mm-hmm.
If A is less than equal to B,
Okay, so 1 second. So order relation is relation R. I'm sorry, so I'm just being a disorganized now. Is a relation R on S crosses? Yeah, please say A comma B is an
hello,
R.
am I audible?
Yes, yes, yeah, please say.
Yeah. If A is less than equal to B and B is less than equal to A, then A is equal to B.
Right. So you must, yeah, that's right. The same thing as saying that if A comma
Where less
B,
than equal to is basically the relation, which basically
yes,
comes from the usual relation on R.
exactly, yeah, the usual relation. So this is how you would want any kind of order to be. Okay. And R and Q are not the only kinds of things. There are many other sets which have order. Okay, which we may not imagine in the beginning. Okay. So really, but really what this can be a partial order also, right? So when we usually say order in analysis, we will usually mean total order. Even though a lot of stuff that we do here will can be used in partial in places where there is only partial order. Okay, but total order means that for any a and b, right, for all a comma b in S, okay, either, so this is another thing which you have to mention. Okay, either a comma b is true, which means either a comma b is in R, or b comma a is in R, right, for a or a all a comma b where a is not equal to b. So this last condition is important because this really forces us to have a total order. Okay, every two elements must be related. All right, very good. So now let's come back to our thing. Okay, if S is an interesting set, okay, then the following must happen. Of course, S has order. That's clear. We want it to have order. So if S is an interesting set, then if X comma Y is in S, okay, then there must exist a Z which is in S such that X is less than Z is less than Y. Or we can just start with X less than Y here. So I think this is what I think Cyan was saying about density. Density property is actually very, very important. So maybe we can use denseness to actually define Q. I don't know. With some conditions, obviously, we will need it. Okay, some more conditions. But anyways, that's possibility. This is called the denseness property. Okay, we will define denseness in more detail and try to study interesting dense sets of non-obvious dense sets of R maybe. But for the time being, this. So is it clear to everyone? This is certainly a property that you would want your set to have. Any set on which you're doing analysis, if it doesn't have this property,
Um,
then mostly it doesn't make much sense to do analysis on it.
then, hello.
Yeah, please.
You have said that if X is less than Y, then there exists a Z. Uh,
Mhm.
mm, does this make sense in the sense that if we have a Z which is in X and Y, that must be in S. Dense means more
Yeah, yeah, yeah. No,
in the
I
compact
understand
sense.
what you're meaning. Yeah. So what I have defined here, this is denseness, not the exact definition of denseness. Right. So the exact definition of denseness, we obviously need to have two sets, right? We need to have a
Yeah,
set
in
S
which
and
it
set
will be
yeah.
dense.
So you would have to say all that. That's right. That's right. You would say S in density R if any X comma Y in R, there should be a Z in S and so on. That's right. But no, but we're just trying to understand it on an intuitive level right now. Okay, that any set would should roughly have this kind of property. Okay, so yeah, okay, we can say. But you see, this is also the definition of a dense set. This is actually a precise definition. It's a precise definition. So if you just want to say whether a set is whether an order relation on a set is dense or not, then this is the definition. The usual definition, the other way in which denseness is interpreted is if some set is dense in another set, then that's more interesting definition, and that's more interesting use in analysis. But this is also a correct definition for a dense set or a dense order on a set. So this is certainly one of the properties that we would want our set to have. So with this definition, Q is a dense set. Okay, Q is a dense set. That's clear for everyone. We all know that, right? If you take two rational numbers, you take their average, it's in between, it's there inside between. So obviously Q has the property. But the problem with this is there's another problem, right? That so it's a following problem here. There are subsets of Q. There are bounded subsets of Q. Bounded subsets of Q that do not have maxima. That do not have maximums in Q if you just remain in Q. Okay. Now, this is the problem. Now, see, the natural numbers do not have this problem. You get my point. So, if you take a subset of the natural numbers, let's say if S is a subset of N and S is bounded, then clearly S will have a maximum element, right? So, S is very good in this sense that any bounded set has a maximum element. Is that all right? Okay, right? Any bounded set of natural numbers has a maximum. So it is a very good set. I mean, subsets of S, bounded subsets of S are good in that sense. They have a maximum, they have their endpoints. But that is not there in Q. Can anybody give me an example of a bounded subset of Q which doesn't have a maximum?
Yeah, if we take, let's define a subset, say S of Q by x belongs to Q if x square is less than 2.
Uh-huh. So S is defined as x square is less than 2 and x belongs to Q. Okay. Oh, no, no. Okay. So the example you're giving, this is a much more delicate example. Okay. Okay. But right now, I'm not asking this is a much deeper example. I understand. But I am asking a very simple question. Okay. I'm asking just an example of a subset of Q which doesn't have a maximum.
So we can take the open interval 1 to 2 and rationals between them.
Exactly. Okay. So, Subham, do you see? I know the example you're giving. This is a very profound. I mean, this leads to Supremum and so on. I understand. But my question is much simpler. Okay, that sets which do not have maximum, clearly. But the problem with, but you see, the good thing about this set that Noel is saying that even if it doesn't have a maximum, we can we can kind of put the maximum in it. There is a maximum outside the set, that though that doesn't make sense, right? But you can add a q in this and you can get a maximum. Okay, so what I'm trying to say is that 1 comma 2 intersection q. So number one bad thing is that maximum is not available. Okay, maximum not available. Okay, but what is a good thing? Good thing is that, so if maximum is not available in the set, is not available, which means it's not in the set, maximum has to be in the set by definition, then what's the next thing that we can do? Well, the next thing that we can do is we can ask for the following. We can ask for if the set of upper bounds, so let's call this S, if the set of upper bounds of S has a minimum. See, this is the next best thing that we can expect, isn't it? So if you have a bounded set and it does not having a maximum, then you can take all the upper bounds of the set S, meaning that take the collection of elements which are bigger than every element in S, right? Upper bounds. And in that collection, you can ask for a minimum. That's the next best hope, right? Min max principle, min max kind of argument, right? So this. And to the answer to the second one is yes, you can do that. 2 is that element. 2 is the minimum. So, so 2 satisfies condition 2. So that's why even though some sets do not have maximum, you can always introduce the maximum and make the set what is called closed. That's why it's called a closed interval. Okay, is that okay, right? So this is a really important entity. This becomes a necessity sometimes when maximum is not there in the set, because we can't change the set in a sense that we can introduce it. Okay, never mind. Now, however, there are sets, and what example has been given by Subham here, there is a set for which even condition 2 is not satisfied. 2 is also not satisfied. So these are worse kinds of sets. They really showcase a deep inadequacy of the rational numbers. I'll say this in more detail right now. But before that, we can see that there is a give and take going on over here somewhere. See, the why are we not even having maximums or not having minimum of all upper bounds? Why are these kind of problems happening in Q? Because we tried to solve another problem of making natural numbers dense. Natural numbers were not dense, but they had this thing that every bounded set has maximum. So to solve the denseness thing, which was even a more acute problem, we made the natural numbers dense bringing in Q, right? We had more complicated quantities like fractions, so we built a Q number system, and that had denseness. So that problem was solved. But as usually what happens in math, right? When you solve one problem, usually the other problem creeps up, and that's why, because when now more things are available in the set, right? So there are more possibilities of not having, of having not having a sink and having an abyss, which is kind of what is going on here in x square less than 2. Even in this, right, if you're standing inside this 1 comma 2 interval, then you can't see the end point on the right hand side. So it's kind of like infinite on the right if if you look at it from inside. And we will show that later, that these sets are like equivalent to 1 comma infinity in some sense. We will show that later. Okay, so let's come to this. So now we can stop worrying about naturals and denseness, because denseness is something which is very fundamentally required. We got it, but now we have created a even bigger problem, to be honest. Okay, that's my perspective of it. So let's come to this set. Okay, so first of all, let me just define this set of all upper bounds, because maybe some people might not be very comfortable with it. So I'll just define it. Okay, so yes, and another thing, in 10 minutes the meeting will end automatically because of a 40-minute limit, which sometimes just starts on its own. So just join immediately after, if the meeting ends. Yeah, okay. In probably 10 minutes it will end. Never mind, let's continue. So yeah, so first of all, bounded set. So can anybody just define this for me quickly? If I won't even write it, just I want to tick it off that everybody is okay with this. Right? What is a bounded set? Or maybe yeah, bounded, I should maybe say bounded subset of a set. Bounded subset of a set S. Let's say Q in this case, right? So S in Q is bounded if there exists a M, okay? If there exists a M such that M is bigger than X for all X in S, and also X is bigger than minus M for all X in S. Basically, there is a bound on both the sides. And we can in fact take the same bound, right? So if the 0 is here and this is a bounded subset, then you can just, if the M is here, you can take minus M. Or if minus M is here, you can take the bigger one, and whatever, you can adjust it. So that's fine. This is a crisper definition of bounded sets. Okay. And what is the set of all upper bounds? I think this is also clear to everyone. Okay, so if S in Q, I still define it, is bounded, then U is, or maybe I can just say like this, then U defined as, Y, such that Y is bigger than X for all X in S. This set U is the set of all upper bounds, okay, bigger than or equal to. Just trying to get the definitions out of the way, okay? Okay, now we know that this set X such that X square less than 2 doesn't have a maximum. That is very clear, right? It doesn't have a maximum in the set. The claim is that it doesn't have a least upper, I mean, it doesn't, the set of all upper bounds also don't have a minimum. Okay, so the minimum, this has a name of the set of all upper bounds. Remember, why are we even studying this? Because if maximums are not available, then this is the next best thing. It's as simple as that. So the minimum of the set of all upper bounds has a name, is called supremum. Okay, it's called supremum. This is just another name so that we can talk about it conveniently. Okay, so now we want to show that this set S that we have below, S does not have supremum, even does not have a supremum. So does anybody want to have a go at this? Yeah.
Can I means I have to first of all S is bounded. Is this clear?
Yes. So S is bounded is
Mm,
clear. So we will take that. Yeah.
Now, now I will show that. Can I work in the reals?
No, that's the thing that people do. Yeah, but that is not allowed for us because at this point we don't know what the real numbers are at all. In fact, we will never know, to be honest,
Okay, okay, okay.
because the real
It is
numbers are just,
bounded.
yeah.
So if it is bounded, so if it has a supremum in Q, say L. Okay.
Okay. Say L belonging to, okay, I'll say small l. I don't want to call it a set. Say L belonging to Q is a supremum. Okay.
Then by the property of supremum, L is greater than equal to X for all X belongs to S.
Mm-hmm. L is
And if hmm,
for all X belonging to S. Okay, so so he's going by contradiction. He's assuming that there is a supremum. Okay, yeah. Go on.
hmm, and this, and if we take any small epsilon greater than 0,
Okay. Take epsilon
then
greater than 0.
then there exists element in the set S, that is there exists an x1 in S, is that this x1 is greater than L minus epsilon and less than equal to L.
X1
This
is
basic.
greater than L minus epsilon. Okay. So, yeah. And it is bigger than and less than L. Okay, fine. So this,
Mm,
so can you explain people why this is happening?
yeah, since L is the supremum, so
Hmm.
it is the least. It is the least upper bound.
Hmm.
So if I take any small epsilon greater than 0, and if I take
Hmm.
so L minus epsilon is basically not a upper bound of
Not
the
an
set
upper
S.
bound, exactly. That's what you should say, yeah, because people catch the words faster, right? So L minus epsilon is not an upper bound because L was the least upper bound, least of all upper
So
bounds. Very good. So there
so
is
it
an
has an
x1.
element in.
Perfect.
Yeah, yeah,
Yeah.
yeah, yeah.
So in between there will be an x1. Okay, go on then. So where's the contradiction? Let's see.
Yeah. So if this happens, mm, now we have the fact that L is greater than equal to S. Like, so if I am able to find an element in S which is greater than L, so I'm done.
Certainly, yeah. If you can find something in X which is bigger than L, then obviously you're done. Right.
Yeah. So L has to be less than 2.
L has to be less than 2.
Less than yeah, yeah, yeah.
Yeah, L is less than 2 we can take. That is obvious. Yes.
Yeah, yeah. So and let us take a wait. I'm just thinking.
So others can also comment here. It's if anyone has any idea. Yeah.
Wait. um,
I mean, another idea.
Okay. So you can also say yes.
So we have x square less than 2. That basically implies that x is between minus 2 and minus root 2 and 2
No, we
union
cannot use root two. We
intersection.
Yeah, but we cannot. Also, okay, fine. Okay, x is between root two and minus root two, and
Yeah,
intersection with
intersection.
q. But the problem
Yeah.
is that we can't use the word root two.
Yeah, that is there.
But still, yeah, that's the problem because root two is not a number for us.
Yeah,
Otherwise,
not
this
in.
proof we can give a proof. Okay,
Yeah,
but I
we
think
can take.
yeah, but so Subham, the problem I think which will happen is that you're trying to show that there is an element which is bigger than L.
The
I
problem
don't
is again with the root 2. I think I'm also
Ha,
considering.
because that's another problem. And also, there's a fundamental thing in the approach that I'm not very sure about, which you're saying. If you want to find something, how can because the straightforward, yeah, maybe indirectly, if you can show, then it's fine. Otherwise, directly you cannot show it because you've already assumed that L is a supremum. So, well, the idea is like this. I'll just say there are many problems like this. But I'll not prove anything right now. Okay, I'll just give the idea, and I want people to write a proof and give it to me. Try to write your own proof. Okay, though this is a very standard result, but it will be good if you can write your own proof. So, see, the point is that L, we want to show that L is not a rational number. We all know that root 2 is there. In our mind, we know root 2 is the answer. But we want to show that there is no rational L which works, right? So you can take two cases, right? If case 1 and case 2. Case 1 would be if L square is bigger than 2 and case 2 is L square is less than 2. If the supremum is bigger than, if the square of the supremum is bigger than 2 or square of the supremum is less than 2. Basically, because in your head, you know that the supremum cannot be bigger than root 2 and it cannot be less than root 2. So it will be easy to get contradictions. But you can't use the word root 2, so you just say L such that L square is bigger than 2. So if L square is bigger than 2 and L square is a rational number, okay, then you can see this is very clear, right? If L, though I will show it by a proof because just saying clear, then you can just say this problem itself is clear. So if L square